I'm Andrew Cannon, and this is my MAE 535 project on solenoids. So two ways to calculate a magnetic field are the Biot-Savart law, or Ampere's approximation. In the case of a solenoid, we can use a summation approach for Biot-Savart or integration approach. Biot-Savart's law states that differential magnetic field equals the current times a differential current element cross product with a unit vector, which is the pointing from the differential current element to the point of interest, all divided by 4 pi r, where r is the distance. One of the instances where we're able to use Biot-Savart's law to analytically solve a problem is in the case of a circular current loop, where the solution is shown there. The summation approach would involve adding up a bunch of these, and the integration approach would involve defining a differential current loop and integrating over the length of the solenoid. But in our case, we're just going to use Ampere's approximation, which states that the magnetic field intensity is the number of turns times the current divided by the length of the solenoid. I've done a demo calculation here. I'm assuming that I'm only using 12 volts, and the internal resistance of my solenoid is about 16 ohms, and that yields a magnetic flux of about 0.016 Tesla. For my project, I'll be using this solenoid that I've wound around along with a steel plunger. If the solenoid is working, it should magnetize the plunger and draw it inwards. So we'll use that to demonstrate that it is in fact producing a magnetic field. The first demonstration is just to show that the solenoid is working. So I'll take this ferromagnetic steel rod and I'll probably put it in so it's about a little less than halfway down the center of the solenoid to begin with. I've got 8 AA's in series here. Should give me around 12 volts. And if I close the circuit, you can see it jumps in. I can pull it out again a little bit. It'll jump right back in, and we can see if we pull it out that it stops just a little bit after the end of the solenoid. Its momentum probably carries it a little further, but that would make sense. We'd expect it not to travel much further than that, as the magnetic flux drops pretty rapidly once it's outside the solenoid. Now I'd like to test the relationship between the current and the magnetic flux that the plunger experiences inside the solenoid. Here I've put a couple of springs on the end of the plunger, and so for a certain amount of force it'll move a little bit, and if we double that force, the displacement should be doubled. So to demonstrate this, we're going to start with 6 batteries here. It's 9 volts total. We're going to have to get in close because my solenoid's kind of weak, and we're going to measure this first displacement. You can see it's a little less than 1 millimeter. Now I've doubled the voltage to 18 volts, which should double the current, which should double the magnetic flux, which should double the force on the plunger and the displacement of the plunger on the springs. So we're going to get in close and line it up. And sure enough, we can see it's moving about twice what it was before, almost 2 millimeters instead of just 1.